Calculate the root mean square velocities of CH4 and N2 molecules at 273 Kelvin and 546 Kelvin. The formula for root mean square is the square root of 3 times R times T divided by M, where M equals the molar mass in kilograms, R equals the molar gas constant of 8.314, and T is the temperature in Kelvin. Starting with the first problem, we want to find the root mean square of CH4 at 273 Kelvin. So we take the square root of 3 times 8.314 times 273 and divide by the molar mass in kilograms. The molar mass of CH4 is 16 grams, so in kilograms it's 0.016. Once you multiply that out, you get 652.2 meters per second. Use the same process for the next 3 problems. To find the root mean square velocity of CH4 at 546 Kelvin, you multiply 3 times 8.314 times 546, since the temperature changed, and divide by 0.016, and you take the square root of that answer, and you get 922.4 meters per second. Same process for N2, except instead of dividing by 0.016, you divide by 0.028, since the molar mass of N2 is 28 grams per mole. So, to find the root mean square velocity of N2 at 273 Kelvin, you multiply 3 times 8.314 times 273 divided by 0.028, and you find 493 meters per second. Same thing for the last problem, except you change the temperature again to 546, and you find 697.2 meters per second. The rate of effusion of a particular gas was measured and found to be 24 milliliters per minute. Under the same conditions, the rate of effusion of pure methane gas is 47.8 milliliters per minute. What is the molar mass of the unknown gas? To solve this problem, we use Graham's law of effusion. Rate A over rate B equals the square root of the molar mass of B over the molar mass of A. In this problem, A is methane gas and B is the unknown gas. So we take the rate of CH4 over the rate of the unknown gas. So 47.8 over 24 equals the square root of the molar mass of the unknown gas over the molar mass of CH4, which is 16. So once you set those equal to each other, you cross multiply, and you find the answer is the molar mass of the unknown gas is 63.47 grams per mole.
Okay, this problem has to do with Dalton's law. So a piece of solid CO2 with a mass of 7.8 grams is placed in an empty container of 4 liters at 27 degrees Celsius. Part A asks what the pressure of the container is after all the CO2 has vaporized. And then if the 7.8 grams of CO2 was placed in the same container, but it had already contained air at 740 torr. Part B asks us what the partial pressure of the carbon dioxide would be then, and Part C asks us what the total pressure in the container after the CO2 vaporizes would be. So for Part A, finding the pressure in the container with just the CO2, first you go from the 7.8 grams, you convert to moles, so you divide by the molar mass, which is 44 grams, and then you multiply across and you get 0.18 moles of CO2. And then you use the ideal gas law, PV equals nRT, to find the pressure. So you know it's 4 liters, it's 0.18 moles, and the temperature is 27 degrees Celsius or 300 degrees Kelvin. If you multiply and divide by 4, then you get pressure is equal to 1.1 atm. Part B asks us whether or not the pressure would change if it was placed into a container that already contained air at 740 torr. And the total pressure is going to change because there's more, it's not just CO2, but the partial pressure of just the CO2 is the same because it's the same mass of CO2, it's the same temperature, it's the same volume, everything's the same for CO2, so the partial pressure of CO2 is still going to be 1.11 atm. To find the total pressure, you have to convert from the 740 torr of air that was already in there to ATM. So you divide by 760 and you get 0.97 ATM. And you add the partial pressure of the air, which is 0.97, plus the partial pressure of the CO2, which is 0.11, and then you get 2.1 ATM. This is an example of Dalton's law, the two partial pressures combined to the total pressure. This next problem involves mole fraction. So the question asks us, the partial pressure of CH4 gas is equal to 0.175 ATM, and the partial pressure of O2 gas is equal to 0.250 ATM in a mixture of the two gases. Part A asks us to find the mole fraction of each gas. Part B asks us if the mixture occupies a volume of 10.5 liters at 65 degrees Celsius to calculate the total number of moles of gas in the mixture. And Part C asks us to calculate the number of grams of each gas in the mixture. So, Part A of the problem asks us to find the mole fraction of each gas in the mixture. You can do this by dividing the partial pressure of the gas over the total pressure. So for CH4, the partial pressure is 0.17 ATM, and the total pressure, if you add the partial pressure of O2 and CH4, is 0.425 ATM. And then if you divide this, you get 0.421. The mole fraction of O2 is the same thing. You divide the partial pressure by the total pressure. So it's 0.250 over 0.425. And then you get 0.588. And there's no units for mole fraction, but one way that you can figure out that you're doing it correctly is if the mole fractions added together equal 1, and in this case they do, so that's all good. B asks us to find the total number of moles of the gas in the mixture if the mixture occupies a volume of 10.5 liters at 65 degrees Celsius. So you have to do PV equals nRT twice to find the moles of each gas, and then you add the moles of the gas together. So for CH4, the pressure is 0.175. The liters is 10.5, equals N is what you're solving for, R is 0.0821, and the temperature is 338. It's the same thing for O2, except the pressure is 0.25 and not 0.175. If you multiply everything and then divide, you get for CH4 that the moles is equal to 0.0662 moles, and for O2, 0.0946 moles. And then if you add these two together, then you get the total moles, which is 0.161 moles. For part C, it asks us to calculate the number of grams of each gas in the mixture. So it's just quick mole to mass stoichiometry. You multiply by the molar mass. For CH4, it's 0.0662 times 16 to get 1.06 grams. For O2, it's 0.0946 times 32 to get 3.03 grams of O2.
Another problem tells us to consider the following reaction. It takes 2 liters of pure oxygen at STP to react completely with a certain sample of aluminum. What is the mass of aluminum reacted? Since we know it's at STP, we know that it's going to be at 22.4 liters per mole and 25 degrees Celsius and at 1 ATM. So we're going to divide the 2 liters of oxygen by the 22.4 liters by 1 mole. Then we're going to use the reaction for a molar ratio to convert it from moles of O2 to moles of aluminum, and then multiply it by its molar mass, which is 26.98 grams, to get 3.21 grams of aluminum is needed to react with the oxygen. One problem for Chapter 5 is, suppose 2 200-liter tanks are being filled separately with the gases helium and hydrogen. What mass of each gas is needed to produce a pressure of 135 atm in its respective tank at 24 degrees Celsius? So first, you're going to use the ideal gas law and manipulate it so you're finding the moles that is needed for each tank, which will end up being 1,107.3 moles. And you're going to use this to multiply it by each gas's molar mass. So for hydrogen, it's 118.4 grams, and for helium, 4,429.2 grams.